Good day, students. Today we will be covering vector spaces. I hope that soon everything will get to normal once this coronavirus madness has subsided. Anyway, let's just carry on with today's lecture. So this is just the outline. I will introduce you to vectors, which will be a revision because you have done that in second year. And we will go through definitions of vector spaces as well as bases. And by the end of this lecture, you should be able to show that a given set is a subspace of a vector space. And we're also going to use cover an algorithm that will show you how to find a dimension of matrix and how to find out the basis of a matrix. Let AI be an element of F, where I goes from 1 to n. Then the ordered n tuple A is a column vector from A1 all the way to AN. Obviously, if you have two vectors, we call it a double. If you have three vectors, it's a triple. But if you go on to n-dimensional space, we just say it's an n-tuple, and such an n-tuple is an n-dimensional vector. If A, an element of n, is an n-dimensional column vector, its transpose is the n-dimensional row vector, denoted by A dash, A1 all the way to AN. If A, B are two n-dimensional vectors and AB is in F, we define their sum by A plus B. This is just to say that if vectors are of the same dimension or matrices are of the same dimension, you can add them. So A plus B is just you add every component of A and every component of B. If C is a scalar and C is an F, we define CA as CA1, CA2 all the way to CAN, which means you multiply every component of your vector with the scalar C. If AB are two n-dimensional vectors with elements in F, the inner product is defined by AB dash. Some textbook will use AB to the power of t. I use AB dash. So the inner product is A1 B1 plus A2 B2 all the way to AN BN. The inner product of two vectors is called the scalar product, and its square root is often referred to as the length or the modulus of the vector. So our inner product space is simply a scalar product because when you take a dot product of two vectors, you get a scalar. If we have AB, an element of F, and these are n-dimensional vectors, they are said to be orthogonal if and only if the dot product of A and B is 0, and if the dot product of A and A as well as the dot product of B and B is equals to 1, they are said to be orthonormal. Vectors V1, Vn in Rn are linearly dependent if and only if there exist scalars C1 all the way to CK, not all 0, such that C1 V1 plus C2 V2 all the way to Cn Vn is equals to 0. Otherwise, they are linearly independent if all the scalars are equals to 0. If you can express 0 as a linear combination of these scalars such that all the scalars are 0, then we say these vectors are linearly independent. A non-empty collection, we go on to vector spaces. A non-empty collection of elements V is said to be a linear space or vector space over the set of real or complex numbers F if and only if there exist two functions, plus called vector addition and dot called scalar multiplication, such that the following conditions hold. So these axioms are just the same as the axioms of the real numbers. So if we have two vectors, x plus y is equals to, two vectors x plus y, because they both face, x plus y will just be the same as y plus x, right? Adding x plus y and then z is the same as adding x to y plus z. And there exists a unique zero element in V denoted by 0, termed the zero vector, such that for all x an element of V, x plus 0 is equals to x. Scalar multiplication is distributive over vector addition for all yx in V and for all cd in F, where cd are your scalars. So we can get rid of the brackets by multiplying by the scalar c. So cx plus y is the same as cx plus cy, and c plus d is the same as taking the vector x and distributing it over c and d. And scalar multiplication is associative for all cd, an element of F, where cd are your scalars and x is a vector. Multiplying out cd times x is the same as c bracket dx. For the zero and unit elements of F, we have for all x an element of V, 0x. When we multiply every vector component with the zero scalar, we get 0 or 0 vector. And 1x is just the same as x. The elements of V are often referred to as vectors. We covered some of these concepts in second year, so I'm not expecting these to be completely new for you. Let Vn denote a generic n-dimensional vector space over F, and suppose that Ai is an element of Vn. If any vector in Vn, say b, can be written as b is equals to ci Ai, where Ci is in F, we say that the set Ai, all the way from 1 to m, where m is greater or equals to n, spans the vector space Sn. For instance, we can write B as a linear combination of the scalar multiples and a vector, and vector A. A basis of a vector space Vn is a span of the space with minimal dimension, that is, a minimal set of linearly independent vectors that span Vn. These concepts will be clear as we do examples. A set S is equals to u1, u2, all the way to un of vectors is a basis of V if it has the following two properties. If S is linearly independent, right? If you have a set of vectors and such vectors are linearly independent, you can say that they span they span the set S. They span the set V, and the basis also, and we say S spans V. S spans V simply means that if we take any vector in V, we can express it as a linear combination of the vectors of S. For instance, the vectors 1, 0 and 0, 1 span R2, in a sense that if I take any vector in R2, I can express it as a linear combination of the vectors 1, 0 and 0, 1. A vector space V is said to be of finite dimension. Dim V is equals to n if V has a basis with n elements. If the vector space V does not have finite basis, then V is said to be of infinite dimension. A set of vectors u1, u2 all the way to un, this un should be bold-faced just to show that we're dealing with a vector, not the scalar, is a basis of V if every V in V can be written uniquely as a linear combination of the basis vectors. This is what I've just said in the previous slide. We have theorems here that will help us in establishing if a set of vectors is a basis or not. Let V be a vector space of finite dimension n. Then any n plus 1 or more vectors are linearly dependent. Any linearly independent set S equals to u1, u2 all the way to un with n elements is a basis of V. For instance, number 1 simply says, if we have 3 vectors, right? If we have a vector in Rn, in R3, and 4 vectors in R4, those vectors cannot form a basis of our vector that is in R3. So if we're in R3, we need 3 vectors in R3 to span our 3-dimensional space. Any spanning set T, V1, V2 all the way to Vn of V with n elements is a basis of V. Suppose S spans a vector space V, then any maximum number of linearly independent vectors in S form a basis of V. Suppose one deletes from S every vector that is a linear combination of the preceding vectors in S, then the remaining vectors form a basis of V. Let V be a vector space of finite dimension and let S be u1, u2 all the way to ur, be a set of linearly independent vectors in V, then S is part of the basis of V. That is, S may be extended to a basis of V. So we can just go through these examples to make all these concepts clear. So here we have 3 vectors in R3. V1 is 3, 0, negative 6. And V2 is negative 1, negative 4, 1, 7. And V3 is negative 2, 1, and 5. we need to establish if V1, V2, and V3 are bases for R3. As in the previous slide, in order for these sets of vectors to be bases of R3, first of all, they must be linearly independent. How do we find out that these vectors are linearly independent? We form a matrix out of these vectors. We form a 3 by 3 matrix and we find the determinant. If the determinant is non-zero, then we say that these vectors, these 3 vectors, form a basis for R3, or they span R3. If we can just go back to our definitions. A set of vectors is a basis of V if it satisfies either of these two properties, if S is linearly independent and if S spans V. In order to find out if these vectors span R3, it means that we want to know if any vector in R3 can be expressed as a linear combination of these 3 vectors. If we go, this is what I did on the slide. I have V1, V2, and V3 are linearly V1 and V2 are linearly independent if their determinant is non-zero, not zero. If it's 0, it means they're linearly dependent. If you can just scratch that out, that should be non-zero. I formed the vectors out of, I formed a matrix A out of my vectors, and then I calculated the determinant, right? After when I do all my workings, the determinant is 6. Clearly 6 is not equals to 0, which means my vectors V1, V3 form a basis for R3. Alternatively, you can take any vector in R3 and establish if you can express it as a linear combination of V1, V2, and V3. So if I take any vector, then my text got cut here, so the answer continues on the other slide. So if I take any vector in R3, I don't care what it is. I mean, it can be A, B, C. I don't know what it is. It's just any vector in R3. I mean, you can use any alphabets. It could be D, E, F, but I just take any vector A, B, C, right, which is any vector in R3. So I need to express this vector as a linear combination of my vectors V1, V2, V3. To express it as a linear combination, I just say V is equals to X V1 plus Y V2 plus Z V3, where X, Y, Z are scalars. So my task here will be to find X, Y, Z. If I can find non-zero X, Y, Z, it means that I can express V as a linear combination of V1, V2, V3. In order to do that, I will have to solve this. I will have to solve X, Y, Z using matrix methods. For instance, this system can be, this equation can be written in a matrix form as follows. And then in order to solve this, it means that I need to reduce this into echelon form and use backward substitution to solve for X, Y, Z. And clearly you will see that X, Y, Z will be solved in terms of A, B, and C. So if I can get such X, Y, and Z, it means that I can express any vector in V as a linear combination of V1, V2, and V3. So here we have determined whether these 1, 2, 3, 4. These 4 vectors in R4 form a basis for R4. Likewise, we're going to form a matrix out of these vectors, right? This is just a guide solution. You form the matrix out of these vectors, find the determinant of these vectors. If the determinant is non-zero, then the vectors form a basis for R4. I don't know yet if this determinant is non-zero. I have to work it out. I will leave this as an exercise for you to work out the determinant. And if it's non-zero, it means that the vectors form a basis for R3. For R4. And then we have question: determine whether or not each of the following form a basis for R3, right? Number 1 and number 2. For number 1, as we saw that we had 2 vectors in R3, so we only have 2 vectors in R3. So such vectors cannot span R3 because they are smaller than the dimension space, right? It means we cannot take any vector in R3 and express it as a linear combination of these vectors. And then we in R3 and we have 4 vectors in R3. Obviously one of these vectors is linearly dependent, which means it cannot form a basis for R3. This just follows straight from the theorem that we had from the previous slides. So all these vectors 3.1 and 3.2, they do not form a basis for R3. This is just a hint in terms of how to approach this problem. If you want to know if the vectors are linearly independent, you find the determinant of the system. Or you can, once you can find the determinant of the system, it means you can reduce such a system to echelon form, right? If the reduced system has a row of zeros, then the vectors do not form the basis. From there you can conclude, if you have a row or column entirely made up of zeros, it means that your determinant will be 0, which means that your set of vectors will not form a basis. It means they're linearly dependent. And we move on to subspace of a vector space. This concept is very important. In a test, I can ask you to establish if a given set is a subspace of a vector space. So if we have, if Vn is a vector space, right, let Vn be a vector space and Pn be a subset of Vn, it means that Pn is entirely contained in Vn, if you remember that from set theory. In a sense that if B is in Pn, it automatically follows that B is in Vn. That's just the pure meaning of, a pure definition of a subset. If Pn is also a vector space, then it is said to be a subspace of Vn. And all the concept of spanning basis sets and dimension applies to Pn as well. So we have a theorem here. Suppose that W is a subset of a vector space V, then W is a subspace of V if it satisfies the following conditions. The zero vector belongs to W. For every UV in W and K in K, the sum U plus V is in W, right? And if we were to multiply U plus V with K, a scalar, then KU plus KV should also be in W, right? And the multiple KU should also be in W. This is the same ideology follows. Remember when you wanted to establish that a given set is a metric space, it had to satisfy three properties of a metric space. The same thing applies here. In order to establish that a given subset of Vn is a subspace, it should satisfy these three properties here. And it is your task. Your task will be to establish that these three properties are satisfied. And if they are all satisfied, you can say that a given set is a subspace of a vector space. So we have examples here. We have two examples. Given V1 and V2 in a vector space V, our set is defined as H. H is equals to span V1, V2. Show that H is a subspace of V. Obviously, if H is span V1, V2, it means any element of H is spanned by V1 and V2, right? So I have worked it out in the next slide. For instance, the zero vector is spanned by V1 and V2, right? I can express 0 as a linear combination of x V1 plus y V2, where my scalars x and y are all equal and they equal to 0. Therefore, 0 is in H because 0 is spanned by V1 and V2. Now I need to take two elements in H, right? This is a definition of a subspace. Remember, in order for a subset to be a vector space, the zero vector should belong to such a set. So I've already proved that the zero vector belongs to H. Now it remains to show that if I take two vectors in H and I add them up, I get a vector in H. So now I take two vectors in H. Let A be in H. Obviously, the definitions of set theory must come into play here. I did say that if I tell you that a set is entirely made up of apples, right? I have a bowl of apples, it's a set. And if a fruit is in that bowl, I can just conclude that such a fruit is an apple. The same applies here. If A, B are all in H, A, B should look like elements of H. So A will be, if A is in H, it means that A is spanned by V1 and V2, where X and Y are elements of real numbers. Remember, that's a definition of a spanning set. It means that A can be expressed as a linear combination of V1 and V2, where X and Y are scalars. I also claim that B is in H. If B is in H, it means that it is spanned by V1 and V2, where W and Z are scalars. Now I add these two elements. If I add them, I'm hoping to get an element in H. I add a plus b. A is x v1 plus y v2. B is w v1 plus z v2, right? And then I take out a common factor, which is v1 in this case, v1, x plus w. Remember, x and w are scalars. I add two scalars, I get a scalar. So this is a scalar. And I have v2. I take v2 as a common factor. I add y plus z. Y and z are scalars. The sum should also be a scalar. So clearly, a plus b is spanned by v1 and v2, where x plus w and y plus z are scalars. So we conclude that a plus b is in H. Why is it in H? Because it is spanned by v1 and v2. It takes the form of all the elements in H, the way H is defined. One more thing I just want to explain to you guys is that my set keeps on changing. I can change how my set is defined, but the technique of establishing that as a given subset is a subspace of a vector space remains the same. I've come across cases where students will just use a definition of previous problems. I mean, using a definition of a set of a problem that we did in class. Obviously, you will just get 0 for that because the definition of a set keeps on changing. Given how your set is defined, then you must carry on to show that such a set is a subspace, right? And now I have proved number 2. I have proved the second property of this theorem here. If I have two vectors uv in W and k a scalar, the sum is in W. So it remains to show that a multiple of a sum, you can either say ku plus kv, should also be in W. Even if the multiple k, you should also show that ku, a scalar multiple of a set that is in W, is also in W. So we call this closure under multiplication, and this is closure under addition, right? So here I take a multiple k of a plus b. It's ka, where k is a scalar. That's very important. Ka plus b is just the same as kx plus w v1 plus ky plus z v2, right? I multiply out two scalars, obviously I will get a scalar, right? So obviously ka plus b is also spanned by v1 and v2, and I conclude that ka plus b is in H. So this set is closed under scalar multiplication. For instance, I could have even taken just an element a. Remember, my a is defined as x v1 plus y v2. Ka will just be kx v1 plus ky v2. Kx and ky are all scalars, which means that ka is also spanned by v1 and v2, and I can conclude that ka is also in H. So ka is also in H, which means that I have achieved closure under scalar multiplication as well. So you can either show me that ku plus v is in W, or just ku is in W. You can do either or, then I'll be convinced that a given subset of a vector space is a subspace. And then I can move over to number 2. It's another example. Here H is defined differently here. Now my H is defined as A minus 3B, B minus A and B, where A, B are arbitrary scalars in the sense that I don't know what they are. They can be 1, 2, whatever the case. H, okay, that's just another way of defining H. So I need to show that H is a subspace of R4, right? Obviously H is in R4 because it's a vector with 4 components, 1, 2, 3, and 4. So in order to show that H is a subspace of R4, H should satisfy all these 3 properties. Okay, this is my H, and this is another way of writing H, right? A, B. For instance, when I multiply A, I get A minus 3B. That's the first component. Negative A plus B is the second component. The third component is just A and B is 0. The fourth component is just B and A is 0. So this is another way of writing my set. And if I write it in this way, I can clearly see that my set is spanned by 2 vectors. This vector here in R4 and the second vector, which is also in R4. Recall that A and B are just scalars, right? So we must show that the 0 vector, obviously our 0 vector should be in R4. We must show that it is in H. Clearly, I can write 0 as this set here. The 0 vector is spanned by these 2 vectors here, right? In this case, my vectors are given as 1, negative 1, 1 and 0, and negative 3, 1, 0, and 1, where AB is equals to 0. If A and B are equals to 0, it means that these are this will be just a 0 vector, right? Clearly 0 is in H because 0 is spanned by these 2 vectors in R4. So I did show the first property of a subspace. It remains to show 2 properties, which is closure under addition and closure under multiplication. Now I take 2 vectors in H, right, which will be X and Y. I let X and Y be in H, right? My Y is, obviously if X and Y are in H, it means that Y should be spanned by these 2 vectors here, where C, D are just arbitrary scalars, right? So what I have is Y and X. If X is in H, it means that X is also spanned by these 2 vectors, where A and B are just arbitrary scalars. So I add X and Y together to get, obviously when I add these together, I take these vectors as common factors. I add A and C, right? And then I take this first vector as a common factor. I add B and D, and I take another vector out as a common factor, right? Obviously A, B, C, D are scalars. I add 2 scalars together, I get a scalar. I add another set of 2 scalars together, I get a scalar. So A plus C and B plus D are all in R. So I conclude that X plus Y is spanned by my 2 special vectors here. So this example is the same as the first one. It's just that in this case, my vectors v1 and v2 are given. So I conclude that x plus y is an H. So I have achieved closure under addition. It remains to achieve closure under scalar multiplication. With regards to closure under scalar multiplication, my solution is got cut here. Does not continue. But I can just tell you what we can do, even if I have not written the solution. For instance, in this case here, in order to show closure under scalar multiplication, I need to multiply y by k, where k is a scalar. Obviously, when I multiply y by k, I get ky, right? Then my task is to show that ky is an H. Obviously, when I multiply by ky, I get ky, kc, right, plus dk with all these vectors here. And clearly kc, these are scalars. Kc will be a scalar. Kd will also be a scalar. So it is clear that ky will be in H because ky is spanned by 1, -1, 1 and 0, as well as -3, 1, 0 and 1. So that's how I will show scalar closure under scalar multiplication. Alternatively, you can multiply this x plus y by k, right? You get kx plus ky, and then you will prove that kx plus ky is an H, which is sufficient to say that we have achieved closure under multiplication, under scalar multiplication. And then we have few more examples that we can do. We are given the vector space, which is R3. We need to show that U is a subspace of V, where U is defined as ABC, right? U is a vector in R3. As you can see, it has 3 components. And the way it is defined in such a way that A is equals to B, B is equals to C. As you can see here, my sets are defined differently. In this case, my set U is an R3, where every component is equals to each and every single component, right? So this will be 1, 1, 1, 2, 2, 2. That's just how this vector, how this set is defined. So if a set is defined this way, and it happens to be a subset of V, right? Now I need to check if it satisfies all my 3 properties. If it satisfies all these 3 properties, then I can conclude that U is a subspace of V. So I have this in my solution. So let X be in U, right? I take any vector X, right? Then X1 is equals to X2 is equals to X3. That's just how the vectors of U, how the set U is defined. It's like with the fruit example, I know I have a bowl of apples, and when I say the fruit is in that bowl, obviously you can say such a fruit is an apple. So we say X is in U, it should automatically follow that every component is equals to the other, right? Hence the 0 vector in R3 is in W, right? If I talk about the 0 vector in R3, it means that every component is 0 in that element. Is 0 in R3. So the 0 vector in R3 is clearly in U, because 0 is equals to 0 and it's also equals to 0. So every component is equals to 0, right? Now I take two elements in U, right? X, Y in U. By the fact that these are in U, it means that all the components are equal, right? X1 is equals to X2, and in turn X2 is equals to X3, right? Y1 is equals to Y2 is equals to Y3. Now I add these elements together, right? When I add them, obviously to add two vectors of the same dimension, you must add all of their components. So if I add x1 plus y, okay, I get x1 plus y1, x2 plus y2, x3 plus y3, right? Clearly, x1 plus y1 is equals to x2 plus y2, which is equals to x3 plus y3, because x1 is equals to x2 and is equals to x3, and y1 is equals to y2 and is equals to y3. If this is not clear, you can just take actual numbers. For instance, if x is 1, right? Every component is 1 for x. I have 1, 1, 1. And every component is 2 for y. I have 2, 2, 2. If I add 1 plus 2 is 3. 1 plus 2 is again 3. 1 plus 2 is 3. So if that's the case, it means that the sum, it means every component of the sum should be equal. And that follows from the fact that x1 is equals to x2 is equals to x3, and y1 is equals to y2 is equals to y3. So I have achieved closure under addition, right? So the second property is satisfied. Now it remains to show closure under scalar multiplication, which will just be cx, right? Remember, my x is equals to x1, x2, x3, where x1 is equals to x2 is equals to x3. Obviously, if I multiply, if all the components are equal, and I multiply every component by a scalar c, I will also get that c, every component in the resulting vector cx will be equal, which follows from the fact that x1 is equals to x2 is equals to x3. Therefore, cx is in w, not just x, but cx is in w, which means I have achieved closure under scalar multiplication. Alternatively, I could have just multiplied x plus y by c, and in that case I would have also achieved closure under scalar multiplication, and we conclude that U is a subspace, right? Is a subspace in the sense that the zero vector is in U. U is closed under scalar multiplication, and it is also closed under addition. And we also have a vector space here, number 2. A vector space of n by n matrix, of n by n matrices. We need to show that W1, a subset of all upper triangular matrix, is a subspace of V, right? So obviously W1 is will be a subset of n by n matrices. Our task is to show that it's a subspace, which means we need to show that this vector, this set defined as a set of all upper triangular matrix, right? We need to show that such a set satisfies the three properties of a subspace. So what we do is, how the set is defined is very important. So in this case here, this is how W1 is defined. It's a set of all upper triangular matrix in a sense that every entry below the diagonal is equals to 0. Remember your upper triangular matrix. The upper triangular matrix is defined in a sense that above your diagonal, you have non-zero numbers, and everything underneath your diagonal will be 0, which happens at this stage, right? So we have Aij is equals to 0 for all I greater or equals to j. For I greater or equals to j, those are the entries of your matrix that are 0 or below your diagonal. Obviously, with regards to the 0 matrix, the 0 matrix will be 0 for all ij, right? I mean, the 0 matrix is 0 everywhere. We can conclude that Aij0 is equals to 0 for I greater or equals to j. So the 0 matrix does satisfy the property of an upper triangular matrix because everything below the diagonal of a 0 matrix is 0 as well. So we conclude that this M naught, or the 0 matrix, is in W1, right? Now we need to take two sets in W1, right? Let C be in W1 and B in W1. If the C and B are in W1, it simply means that they are upper triangular matrices. They need to satisfy, they should conform with the properties of such a set. K and B, this is how it's defined. I add these together, Cij plus Bij, right? These are my upper triangular matrices. Obviously, if I add them together, Cij plus Bij, obviously we assume that they are of the same dimension. That's why we can add them. We will get that all my elements that are below the diagonals will be 0 for all I greater or equals to j, right? Then I can conclude that C plus B is in W. So I have achieved closure under addition, right? Now it remains to achieve closure under scalar multiplication. I multiply C plus B with K, I get KCij plus KBij. As you remember, if this is a scalar, I can multiply every component of my matrix with this scalar, right? And this will be 0 for all my K will be 0 for all elements that are below the diagonal, because I already know that Cij is a diagonal matrix and Bij are all diagonal matrices. So this product K, C plus B will be in W. And if I have Kc as well, Kcij will also be 0 for all I greater or equals to j, which simply means all the elements that are below the diagonal will be 0. And if that's the case, I can conclude that Kc is in W1. So I have established that the 0 vector is in W1. I also have established that if I take two sets in W1 and I add them together, I get the set to be in W1. And I've also achieved closure under scalar multiplication. Then I can say W1 is a subspace of Mn by n. Okay, and I do have few more examples. So we did number 1 and number 2. Now we need to show that vectors u1, u2, u3 span R3. I'm not going to do this example because we've done quite a number. I've explained this in previous example. So what you need to do here is to take any vector in R3 and show that such a vector can be expressed as a linear combination of u1, u2, u3, or form a matrix out of u1, u2, u3, find the determinant. If the determinant is non-zero, we say that u1, u2, u3 span R3. So in a test, I remember I used my second years used to be very confused. In a test, I'll be pretty much clear in terms of what to do. I can just ask you to express u1, u2, u3 as a linear combination of any vector in R3. After you have expressed u1, u2, u3 as a linear combination of any vector in R3, then I can ask you to find the scalar multiples of your linear combination, right? Obviously, such a question, if I ask it that way, it will worth more marks than simply just asking for the determinant. But if I just say show that vectors u1, u2, u3 span R3, if you find the determinant to be non-zero and you say that the vectors do span R3, I will accept that. It is still correct. And then we have here, explain why the vectors u1, u2, u3, u4 form a basis for R4. That's just another way of asking what the question that I've asked in question 3. Obviously, in this case, you will also form a matrix out of these 4 vectors in R4 and calculate the determinant. If the determinant is non-zero, you just say u1, u2, u3, and 4 form a basis for R3, right? And then we have if dimensional p and t is equals to n plus 1. Okay, this is a polynomial space, right? It's a dimension of a polynomial, right? What can you say about the polynomials below? 1 t minus 1 dot dot t minus n, right? So obviously these polynomials here, they can also form a basis for the polynomial space, right? So if remember, a polynomial can be expressed as 1 plus x squared, right? So if you have 1 plus x squared, the dimension of such a polynomial will be 2, and 1 plus x squared will be a linear combination of such a polynomial with dimension 2. So that's all we can say about these other polynomials. Given 4 vectors in R3, okay, 1, 2, 3, 4, what can you say about these vectors? What we can say about these vectors is that they do not span R3, because we have a 3-dimensional space with 4 bases. It means one of them should be linearly dependent, which means they cannot span R3, which also means that they do not form a basis for R3. Okay, here we have algorithms or methods that are used to find basis of a matrix, right? So these are just steps, but in order for steps to make sense, we need to do 1 or 2 examples. So what I'll do is we'll go through these algorithms, and after going through them, we'll do 1 example. The algorithms below are used to find bases of vectors. Say you are in Vn and we want to find a basis for the subspace W of Vn spanned by the given vectors. So what we do is you form the matrix M whose rows are the given vectors, which it simply means that if you have a set of vectors, you form a matrix out of them, and you row reduce M. Row reducing a matrix is something that we covered in second year using Gaussian Jordan elimination, or Gaussian elimination, right? Once you have performed a row operation on your original matrix, the resulting matrix will be a row reduced one, right? So the output will be the non-zero rows of the echelon matrix, right? And then we have the casting out algorithm. In the casting out algorithm, you also form the matrix whose columns are the given vectors, and you row reduce M to echelon form, right? For each column K in echelon matrix without a pivot, you delete that one. And the output is the remaining vectors corresponding to column pivots. And such columns, right? All the columns with pivots in them form the basis of a column space, right? But then, with regards to when you, with the basis for the row space, all your non-zero rows of the echelon matrix form, they form a basis for your row space. So in order for all these concepts to be clear, we need to do an example, which is in the next slide, right? I'll do number 2 and you can do number 1 as an exercise, right? With regards to number 1, we have W is the subspace of R5 spanned by the following vectors U1, U2 all the way to U5. Find a basis for the column space and find the dimension. Obviously, what you're going to do is to form a matrix out of these vectors. After forming a matrix, you row reduce your matrix into echelon form. Once your matrix is reduced into echelon form, all the rows that correspond to the non-zero rows, right, will form your basis of the row space. But now all the columns with pivots in them will form a column space, and your dimension will be the number of your non-zero rows, the dimension of a matrix. Now, with regards to number 8, these are quite large systems. For instance, in a test setting, I'll probably give you a 4x4 matrix, not a 5x5, because it will take you time to reduce such a system to echelon form. But if I do give you a 6x6 or a 6x5 or a 5x6, I will row reduce the matrix for you, like in example number 2. In example number 2, we have this matrix here, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. It's a 5x6 matrix. Obviously, it's not impossible, but it's a little time consuming to reduce it to echelon form. So in a test, I will give you a row reduced echelon form of a matrix. So in this case, the row reduced echelon form of my matrix is B, right? So we need to find the, obviously if I reduce the matrix for you, such a question will worth less marks. But if you reduce it for yourself, it will be more marks. So this question is very popular in past test papers. So you should do yourself a favor to understand this. That's where you can collect marks in an exam. But obviously sometimes I do get disappointed. What we do here, I have reduced the system for you. What you need to do is to find the basis of the row space of A, right? The row space. So obviously, once my system is reduced to echelon form, the rows that form a basis are the non-zero rows. So in this case, my non-zero rows will be, they correspond to the original matrix. So what I've seen sometimes in tests, students will give me the reduced form. Like they will give me 1 2 1 3 1 2 0 1 3 1 as the basis of the row space. But preferably, I will prefer you to read your row space in an original matrix. For instance, I want it to be 1 2 1 3 1 2 2 5 5 6 4 5 3 7 6 11 6 9. That's what I'm looking for. But normally some students will just give me the row reduced form of the rows. I will take that because by definition these two matrices are equivalent. But preferably I prefer you to read these rows in the original matrix, right? And now find each column CK. That is a linear combination of each preceding columns of A. So here what you need to find is, it's the opposite of your basis. I'm not looking for basis because remember, your basis cannot be expressed as a linear combination of other your basis column space cannot be expressed as a linear combination of other columns within a matrix, because by definition our bases are linearly independent, right? So as soon as I say find each column CK that is a linear combination of each preceding columns of A, it means I'm looking for non-bases. For instance, in the algorithm, all the columns with pivots in them corresponds to column bases, right? This has a pivot. I explained this in second year, right? This has a pivot. The pivot is 1. For instance, if we were to circle all the pivots, 1 is a pivot, 1 is also a pivot. We skip here, and 1 is also a pivot, which means columns in the original matrix that correspond to our pivots will form a basis for the column space. So the ones that do not form basis of the column space will be column 3, which will be 1 5 6 10 and 8, right? And this has a pivot. And this column here, which will be column 5, 1 4 6 9. This column can also be expressed as a linear combination of the preceding columns in A, as well as 2 5 9 9 12. It can be expressed as a linear combination of the preceding column. So in other words, these other columns here do not form a basis of the column space. So such columns will be C3, right? C4 as well as C5. They correspond to the original matrix. So, and now we need to find the basis of a column space of A. The basis of a column space of A are all the columns that correspond with the pivots columns on the reduced on our matrix in echelon form. So such columns will be 1 2 3 1 and 2, 25756 and 3611811. So those are the bases for the column space. And we need to find the rank of A, which is the dimension of our matrix. Remember, the rank of A is just the number of non-zero rows of your matrix in a reduced echelon form. For instance, here our matrix, this matrix is in echelon form, and the non-zero rows will be 1, 2, 3. So the rank of our matrix A is 3. Okay, I have everything. Okay, I have 2.1, 2.3, 2.4, rank of A is 3. I have discussed all these solutions and so here what I did is, though it was not asked, like it was not asked in a question, but if I can express these columns as a linear combination of the previous columns, I need to know what the scalar multiples are. In order to find the scalar multiples, it means I have to reduce this system to row canonical form. If you still remember, with regards to row canonical form, the pivot should only be the non-zero entry in a column. So I have to reduce this further, right? Which I did here. For instance, this is my final solution. So this matrix is in row canonical form, right? So in row canonical form, these are my linearly dependent columns, C3, C5, and C6, right? And C3 can be expressed as a linear combination of C1 and C2. So my scalars, I read them off on this column here. So C3 will be negative 5C1 plus 3C2, right? If I have negative 3C1, negative 5C1 plus 3C2 should give me the original C3. Let's see. Here we are. So I have C3 is negative 5C1 plus 3C2. I multiply it out. I get 1, 5, 6, 10, 8. 1, 5, 6, 10, 8 should be C3. 1, 5, 6, 10, 8. It's C3. 1, 5, 6, 10, 8 is C3. So in order to get my scalar multiples, I have to row reduce my system to echelon form. C1 should be negative 4C1 plus C2 plus C4, which is here. C5, negative 4C1 plus C2 plus C4, and C6 should be negative 2C1 minus C2 plus 2C4. Remember, it means that these are linearly dependent columns. I can express them as a linear combination of linearly independent columns, right? That's why I skipped C3, because C3 is linearly dependent. So I use C4 because C4 is linearly independent, right? So all you have to do is to check. With regards to this example, I don't know what went wrong. I got 2, 3, 9, 9, 12, but the original C6 is, okay, 9, 9, 12 were fine, and 2 was okay. 2, was it 5? It should be 5. It should be 5, not 3, which means there's an algebraic error. And then C5. C5 is negative 4C1 plus C2 plus C4. Okay, when I go back to C5, C6, I got this. One entry threw me under the bus. C5. C5, I get 13699. 13699. I should get 4, but I get 13699. There should be some sort of an algebraic error on my in this step here. If you can just redo it and trace my error. But that's what you do in order to get the scalar multiples of the columns that are linear combination of the previous columns. Okay, we have exercises here, right? Okay, these are the exercises. I have the solutions for all of these exercises. I'll just give you a guide in terms of how I got the answers, and you can read the rest of the solutions. So in this exercise, we need to find out the value of h, right? For what values of h will y be in the subspace of R3 spanned by V1, V2, V3, right? So what we're going to do is to express y as a linear combination of V1, V2, V3 and find h, which is what I did here in number 1. I formed a matrix out of those 3 vectors that I was given, and I equated them to y, the matrix. So what I do is I reduce my system into echelon form. Once my system is reduced into echelon form, like here, I have that 12 is equals to -5 plus h, which means I can solve for h, and h is 17. So if h is 17, this system will be spanned by these 3 vectors, v1, v2, and v3. And then show that the set h of all points in R2 of the form 3s plus 2 plus 5s is not a vector space by showing that it is not closed under addition and scalar multiplication, right? So in order for this to not be a subspace of R2, it must violate these 2 properties. It should not be closed under addition and scalar multiplication. So what I do is I take 2 vectors in H as usual. So if I take 2 vectors in H, let A, B be in H, I know for sure that my A is 3, 5t plus 0, 2, because A is in H. And I also take B, which should be 3, 5, R plus 0, 2, because it should look like elements of H, where R and T are just scalars, right? So I add these together, right? A plus B, I get T plus R, 3 and 5, right? 3 and 5 is a common factor. But then if I add 0, 0 plus 0 is 0, 2 plus 2 is 4, right? Now you can see T plus R is a scalar. Here my scalar is 1, right? Because I don't have anything, I can just say it's 1. But now, in order for this A plus B to be an element of H, it should be spanned by 2 vectors, which are 3 and 5, 0 and 2. In my case, A plus B is spanned by 3 and 5 and 0 and 4, which means A plus B is not in H, right? And then if I take a scalar multiplication of any element, my text got cut here, but I'll explain what's in the second component. So if I take a scalar multiplication of any element in H, let's say AK, I know that A is an H, which means A is defined as such. So what I'll do is I get AK, it's ATK times K. K will be 0, 2 will be 2K, this is 2K. And what I get here is that AK is spanned by 3 and 5, as well as 0 and 2K. But it's not in H, because elements of H are spanned by 3 and 5 and 0 and 2. Hence, I conclude that this H, right, is not a subspace of R2. I think that was the question. Where is that? Show that the set H of all points in R2 of the form is not a vector space by showing that it is not closed under addition and scalar multiplication. I did show that, so it's not a subspace of R2. And then number 3, they want to know if R2 is a subspace of R3. Clearly, R2 cannot be a subspace of R3, right? Because first of all, R2 is not even a subset of R3. It does not look like elements of R3 at all. So it cannot be a subspace of R3. Because in order for a given set to be a subspace, first of all, it should be a subset of such a space, right? When it's a subset, then you have to show that it's a subspace. So clearly R2 is not a subspace of R3. And then we have a vector here. Let V be the first quadrant in the xy plane that is given as xy, where every component is greater or equals to 0. Right? If U and V are in V, is U plus V in V? It is. In order to find out why, you can go through my example, right? If I take two elements of V and I add them together, every component of the sum will be greater or equals to 0. And then find a specific vector in U, an element of V, and a specific scalar C such that Cu is not in V. This is sufficient to show that V is not a vector space. Okay, so if I find a specific scalar, right, Cu, I can get -1, right? -1 is a scalar, and if I multiply every component here with -1, I will get that every component is smaller or equals to 0, which violates this, how V is defined. So I would have failed to show closure under scalar multiplication. I have the detailed worked out solutions in the pictures here. Okay, and one more example. Okay, let W be the set of all vectors of, show that W is a subspace of R4. This one I'll just leave it as an exercise for you guys. I mean, we've done many questions that are of this form. I will leave this one as an exercise. Okay, then we have number 2. Okay. So is W is defined as 3, 1, 2, is W in the set V1, V2, V3? How many vectors are in V1, V2, and V3? Right? Okay, the way W is defined, W is in R3, right? So we can say W is in V1, V2. But if this is a set of V1, V2, V3, we can say that W, if this is an already defined set consists of V1, V2, V3, we cannot say W is in this set because W is 3, 1, 2, right? Then how many vectors are in V1, V2, V3? 3 vectors are in V1, V2, V3. How many vectors are in span V1, V2, V3? Only 2 vectors. It's 1, 0, negative 1, 2, 1, 3. Whereas this V3 is a multiple of this set. I mean, it's 2. V3 is just 2V2, right? So it's 4, 2, 6. So V3 cannot be in a spanning set because it can be expressed as a multiple of V2. Is W in the subspace spanned by V1, V2, V3? No, it is not, because this set here, I mean V3 is linearly dependent. So in order for this set to span W, all the vectors should be linearly independent. So we're done with this chapter of vector space. So the most important concepts that I will test in this lecture is that you should be in position to show that a given set is a subspace of a vector space. That's a very important question that you would expect to come out from this chapter. Understand the concept of basis and find basis for a given vector space, right? Be clear on concepts of linear dependence and independence, and establish that a set of vectors is linearly independent, right? And then you should use the casting out algorithm to find the dimension of a matrix and to find the basis, the row basis as well as the column space basis, right, by using the algorithms that were discussed. So in terms of the exercises for this chapter on vector spaces, we used a linear algebra textbook. It's Schramm's outline series. It's not reading, writing, and proving. So what you can do is go to page 163 of the Schramm outlines series textbook in linear algebra, 3rd edition, and do all these exercises for practice purposes. They're not for hand-in. You can do them on your own, but you should expect them. The level of difficulty of the test will be at the level of those exercises. So with regards to Euclidean spaces, I will talk to Mr. Suten to cover Euclidean spaces with you guys, and Euclidean spaces chapter is also on the linear algebra textbook. Thank you very much for listening. Let's hope soon our lives will be back to normal once the whole COVID-19 drama is over. But as you have noticed that every day the rate of infection is going down, so it means soon we'll come back to school. So don't take this as a long holiday, right, or as a mini festive season. I'm sure by the 20th, right, after 28 days, the rate of the virus would have subsided, because I can see the exponential curve is getting smaller and smaller. And these graphs, it's quite interesting that these graphs are exponential graphs. So every day you need to work out, they take the form y is equals to ax, where your x is the domain, your days, right? Y is the number of infection. So y is equals to a to the x. So the aim of the government is to get that a to be smaller than 1, right? Because when a is greater than 1, it means now the infection will explode. But I'm telling you, the a is getting smaller by the day. Once it's 0 point something, we're getting back to our normal lives. Thank you guys for listening, and enjoy the rest of your course, and keep up with other courses as well, just to get your mind off the COVID-19.